The year was 2005. In a gleaming facility in Molsheim, France, a team of engineers stood around a dynamometer display showing a number that had never before been achieved in the history of road-legal automobiles: 1,001 horsepower. This wasn't some stripped-down racing engine or temporary burst of power that would destroy itself within minutes. This was a fully emissions-compliant, warranty-backed engine designed to propel a luxury automobile down public roads for hundreds of thousands of miles. The Bugatti W16 had just shattered a barrier that many thought impossible, and in doing so, it would redefine what humanity considered achievable in automotive engineering. To understand the magnitude of this achievement, we must first grasp what 1,000 horsepower truly means. A typical family sedan produces around 200 horsepower. A high-performance sports car might generate 400 to 500 horsepower. Even exotic supercars of the early 2000s rarely exceeded 600 horsepower. The psychological barrier of 1,000 horsepower represented more than just a round number. It was a frontier that separated the possible from the fantastical. Engineers had long theorized about reaching this milestone in a road car, but the challenges seemed insurmountable. Heat management, reliability, emissions regulations, and the sheer mechanical stress of containing such explosive forces within a passenger vehicle had defeated every previous attempt. The story of the W16 engine begins not in 2005, but in 1998, when Volkswagen Group acquired the dormant Bugatti brand. Ferdinand Piëch, the legendary chairman of Volkswagen, known for his obsession with engineering excellence and his willingness to pursue seemingly impossible goals, had a vision. He didn't just want to revive Bugatti. He wanted to create something that would stand as a monument to human engineering capability. Piëch set forth a series of requirements that made even his most experienced engineers gulp. The new Bugatti must produce at least 1,000 horsepower, achieve a top speed exceeding 400 kilometers per hour, accelerate from 0 to 100 kilometers per hour in less than 3 seconds, and most crucially, it must do all this while maintaining the refinement, reliability, and daily usability expected of a luxury automobile. The fundamental challenge lay in the basic physics of internal combustion. To generate 1,000 horsepower, an engine must burn an enormous amount of fuel and air in a very short time. This creates tremendous heat, extreme mechanical stress, and vibrations that can tear apart conventional engine designs. Most attempts to reach such power levels had relied on racing technology, exotic materials, constant rebuilds, and operating conditions that would be completely unacceptable in a road car. Bugatti's engineers needed to find another way. The solution began with an unconventional configuration. While most high-performance engines of the era used V8, V10, or V12 layouts, Bugatti's engineers, led by Chief Engineer Wolfgang Schreiber, proposed something radical: a W16. This configuration essentially combined two narrow-angle V8 engines side by side, creating a compact power plant with 16 cylinders arranged in 4 banks of 4. The design traced its roots to Volkswagen's VR engine technology, which packs cylinders at a narrow 15-degree angle to save space. By combining 2 VR8 units at a 90-degree angle, the engineers created an engine that was remarkably compact for its displacement and cylinder count. The W configuration offered several crucial advantages. First, it allowed for a shorter engine length than a traditional V16 would require, essential for packaging within a mid-engine supercar chassis. Second, the 4 banks of cylinders provided exceptional balance, reducing vibrations that could compromise reliability or refinement. Third, and perhaps most importantly, the layout allowed for an integrated cooling system that could manage the tremendous heat generated by 1,000 horsepower. But configuration alone wouldn't achieve the power target. The engine needed forced induction and lots of it. The engineers initially experimented with various supercharger and turbocharger configurations before settling on a quad-turbocharged setup. 4 turbochargers, each feeding 4 cylinders, would provide the massive airflow required to support combustion at this power level. The turbos themselves were engineering marvels utilizing advanced materials, including titanium aluminide turbine wheels that could withstand exhaust temperatures exceeding 1,000 degrees Celsius while spinning at over 100,000 revolutions per minute. The turbocharging system presented its own labyrinth of challenges. With 4 turbos operating simultaneously, the engineers had to orchestrate a complex symphony of boost pressure management. Too much boost too quickly would create an undrivable power delivery. Too little would fail to achieve the power target. The solution involved an intricate system of wastegates, bypass valves, and electronic controls that modulated boost pressure with millisecond precision. The turbos were arranged in a parallel sequential configuration with 2 smaller units providing responsive low RPM boost and 2 larger units adding their contribution as engine speed climbed. Cooling this mechanical inferno required rethinking conventional automotive thermal management. The W16 engine featured 10 radiators in total, 3 for engine coolant, 3 for the air-to-liquid intercoolers, 2 for the air conditioning system, 1 for the transmission oil, and 1 for the differential oil. The main engine radiators alone had more cooling capacity than those found in a typical commercial truck. The cooling system circulated 40 liters of coolant per minute at full power, 3 times the flow rate of a conventional high-performance engine. The intercooling system deserves special attention. When air is compressed by turbochargers, it heats up, dramatically reducing its density and limiting power potential. The W16's intercoolers used a sophisticated liquid cooling system that could reduce intake air temperature by more than 100 degrees Celsius. This dense, cool air was essential for achieving the combustion efficiency required for 1,000 horsepower while meeting emissions standards. Material science played a crucial role in the W16's development. The engine block and cylinder heads were cast from aluminum silicon alloy, providing an optimal balance of strength, heat dissipation, and weight. The connecting rods were forged from titanium, offering exceptional strength at nearly half the weight of steel alternatives. The pistons utilized an advanced aluminum alloy with a special coating that could withstand the extreme temperatures and pressures within the combustion chambers. Even the valve springs represented cutting-edge metallurgy, using a special steel alloy that maintained its properties at the extreme temperatures encountered in this application. The fuel system required complete reimagining. At full power, the W16 consumed fuel at a rate that would drain a typical car's fuel tank in minutes. The engine featured 2 high-pressure fuel pumps delivering fuel to 16 direct injectors operating at pressures up to 120 bar. The injectors themselves were specially developed units capable of delivering precise fuel quantities in multiple injection events per combustion cycle, optimizing both power and emissions. The fuel rails were engineered to maintain consistent pressure despite the massive fuel flow demands, preventing the power fluctuations that could occur with conventional systems. Perhaps the most remarkable achievement was making this monster engine comply with emissions regulations. The 2005 Euro 4 standards were stringent, and meeting them with an engine producing 1,000 horsepower seemed paradoxical. The solution involved a sophisticated engine management system with over 100 individual maps controlling fuel injection, ignition timing, and boost pressure based on dozens of sensor inputs. The catalytic converters were specially developed units using advanced precious metal formulations that could withstand the extreme exhaust temperatures while maintaining conversion efficiency. The engine featured a complex secondary air injection system that helped burn residual hydrocarbons during cold starts, a particular challenge for such a large displacement engine. The durability engineering bordered on the obsessive. Every component was analyzed using finite element analysis to predict stress patterns and potential failure modes. The engine underwent thousands of hours of dyno testing, including full power runs lasting hours at a time. Bugatti engineers subjected prototypes to extreme temperature cycling from Arctic cold to Death Valley heat. They ran engines at full power, shut them down immediately, then restarted them cold, repeating this torture thousands of times. The goal wasn't just to survive these tests, but to do so while maintaining consistent power output and meeting all emissions requirements. The variable valve timing system represented another engineering triumph. With 16 cylinders and 64 valves to orchestrate, the system needed to optimize valve timing across a vast range of operating conditions. The continuously variable cam phasers could adjust valve timing by up to 40 degrees, optimizing the engine for everything from smooth idle to maximum power output. This system was crucial for achieving both the broad torque curve needed for drivability and the high RPM power required for the performance targets. The dry sump lubrication system was equally sophisticated. Unlike conventional engines that store oil in a pan beneath the crankshaft, the W16 used a separate oil tank and a complex system of scavenge pumps to ensure consistent lubrication under the extreme G-forces a supercar could generate. The system circulated 60 liters of specially formulated synthetic oil per minute, with dedicated jets cooling the undersides of all 16 pistons. The oil itself was a technological achievement, a fully synthetic formulation capable of maintaining its properties at temperatures that would destroy conventional lubricants. Sound engineering played a surprisingly important role in the W16's development. An engine producing 1,000 horsepower could easily create noise levels that would be both illegal and unbearable. The engineers spent countless hours tuning the intake and exhaust systems to create a sound that was powerful and purposeful without being harsh or drone-inducing. The exhaust system featured specially tuned resonators and mufflers that eliminated unwanted frequencies while preserving the distinctive 16-cylinder sound signature. The result was an engine note unlike anything else on the road, a deep, complex harmony that announced the presence of something extraordinary without resorting to antisocial volume levels. The engine control unit, or ECU, represented the bleeding edge of automotive computer technology in 2005. With processing power exceeding that of many contemporary personal computers, the ECU monitored and adjusted hundreds of parameters thousands of times per second. It coordinated the operation of 4 turbochargers, 16 fuel injectors, 64 valves, multiple cooling pumps, and dozens of sensors. The software alone represented years of development, with algorithms that could detect and compensate for variations in fuel quality, atmospheric conditions, and component wear. The ECU even featured self-diagnostic capabilities that could identify potential issues before they became problems, protecting the engine from damage. The transmission presented its own unique challenges. No existing gearbox could handle the W16's massive torque output while meeting Bugatti's requirements for shift speed and refinement. The solution was a 7-speed dual-clutch transmission, specially developed by Ricardo. This gearbox could execute shifts in less than 150 milliseconds while channeling over 900 pound-feet of torque. The transmission featured its own sophisticated cooling system and used special clutch materials developed specifically for this application. The gear ratios were carefully calculated to keep the engine in its optimal power band while achieving both violent acceleration and relaxed high-speed cruising. Testing and validation pushed into uncharted territory. Bugatti couldn't simply rely on existing automotive test procedures because no road car had ever operated in this performance envelope. The company developed new testing protocols, including high-speed runs at the Volkswagen Group's secret test track in Erlesien, Germany. Here, prototypes were pushed to speeds exceeding 400 kilometers per hour for extended periods, validating not just the engine's power delivery, but its ability to maintain composure under extreme aerodynamic and mechanical loads. The engines underwent the equivalent of 50,000 kilometers of full throttle operation during development, more than most performance cars experience in their entire service lives. The integration of the W16 into the Veyron chassis required extensive engineering beyond the engine itself. The engine bay needed specialized heat shielding to protect surrounding components from the extreme temperatures. The motor mounts were specially designed units that could handle the engine's massive torque output while isolating the chassis from vibrations. Even the engine cover was a carefully engineered component, featuring special glass panels that could withstand the heat while allowing admirers to view the mechanical masterpiece beneath. Production of the W16 engine was unlike anything in the automotive industry. Each engine was hand-assembled by a team of specially trained technicians in a pristine clean room environment. The assembly process took over a week per engine, with multiple quality checks and measurements at every stage. Each completed engine underwent 8 hours of dyno testing before installation, including a full power validation run. The engines were so precisely assembled that Bugatti claimed variance between units was less than 1% in power output, remarkable consistency for such a complex power plant. The cost of developing the W16 engine has never been officially disclosed, but industry analysts estimate it exceeded 1.5 billion euros. This astronomical figure reflects not just the engineering challenges, but the fundamental research required to push into unexplored territory. Every system, from the turbochargers to the cooling pumps to the engine management software, required either significant modification of existing technology or complete ground-up development. The program employed hundreds of engineers and technicians over nearly 7 years, representing one of the most intensive automotive engineering efforts ever undertaken. When the first customer Veyron was delivered in 2006, the automotive world was forever changed. The W16 engine had not just broken the 1,000 horsepower barrier, it had obliterated it while maintaining civility and refinement that seemed impossible. Automotive journalists who had the opportunity to experience the engine were unanimous in their awe. The power delivery was described as a force of nature, yet the engine could idle smoothly in traffic and cruise quietly on the highway. This duality, this combination of savage performance and sophisticated refinement, represented the W16's greatest achievement. The technical influence of the W16 extended far beyond Bugatti. Other manufacturers, seeing that the 1,000 horsepower barrier had been broken, began their own development programs, pushing toward and eventually beyond this threshold. Technologies pioneered for the W16, from advanced turbocharging strategies to sophisticated thermal management systems, found their way into other high-performance applications. The engine proved that with sufficient engineering resources and determination, boundaries that seemed absolute could be overcome. The W16's innovation extended to maintenance and serviceability, crucial considerations for a customer car. Despite its complexity, the engine was designed for relatively straightforward maintenance. Oil changes could be performed without removing the engine, though they required 16 liters of special synthetic oil costing hundreds of euros. The spark plugs, all 16 of them, were accessible without major disassembly. The engine management system included comprehensive diagnostic capabilities that could identify issues down to individual cylinders or sensors, simplifying troubleshooting. However, major service still required specialized knowledge and tools, with only a handful of technicians worldwide certified to work on the W16. Environmental considerations played a larger role than might be expected for such an extreme engine. While fuel consumption at full power was prodigious, the W16 incorporated numerous technologies to improve efficiency during normal driving. The cylinder deactivation system could shut down 8 cylinders during light load cruise conditions, effectively turning the W16 into a W8 for improved fuel economy. The variable valve timing and direct injection systems optimized combustion efficiency across the entire operating range. While no one would mistake a Bugatti for an economy car, the engineering effort to minimize environmental impact within the context of extreme performance was substantial. The reliability of the W16 confounded skeptics who predicted that such a complex, high-stressed engine would require constant attention. In service, the engines proved remarkably robust. Many have accumulated tens of thousands of kilometers without major issues, including extensive high-speed running that would destroy lesser engines. This reliability stemmed from the extensive development, testing, the conservative engineering approach despite the extreme performance, and the use of the highest quality materials and manufacturing processes. The engine's durability validated Bugatti's approach of over-engineering every component rather than pushing everything to the absolute limit. The acoustic engineering of the W16 deserves deeper examination. The sound of 16 cylinders firing in rapid succession creates a unique auditory signature. But managing this sound required sophisticated engineering. The intake system featured specially tuned resonance chambers that enhanced certain frequencies while canceling others. The exhaust system included both passive and active elements, with vacuum-operated valves that could alter the exhaust note based on driving mode and engine load. Inside the cabin, special sound deadening materials and active noise cancellation systems ensured that occupants could hold a conversation at 300 kilometers per hour, a remarkable achievement given the mechanical fury occurring just behind their heads. The evolution of the W16 didn't stop with the original Veyron. Bugatti continued to develop and refine the engine, eventually extracting 200 horsepower for the Veyron Supersport and with 500 horsepower for the Chiron. These increases came not from fundamental redesigns, but from systematic optimization of existing systems. Improved turbochargers, revised engine management software, and enhanced cooling systems allowed ever greater power extraction while maintaining or even improving reliability. The fact that the basic W16 architecture could support a 50% power increase speaks to the robustness of the original design. The manufacturing precision required for the W16 pushed Bugatti's suppliers to new capabilities. The crankshaft, a magnificent piece weighing 45 kilograms, required specialized forging and machining processes to achieve the necessary strength and balance. The camshafts, 4 of them in total, were gun-drilled for weight reduction and manufactured to tolerances measured in microns. Even seemingly simple components like bolts were specially manufactured items using aerospace-grade materials and manufacturing processes. This attention to detail in every component contributed to the engine's ability to operate reliably at its extreme performance level. The combustion chamber design represented years of development and optimization. The shape of the piston crowns, the angle and positioning of the valves, and the precise geometry of the intake and exhaust ports all resulted from extensive computational fluid dynamics modeling and real-world testing. The compression ratio of 9.001 was relatively conservative for a modern engine, but optimal for the boost pressures involved. The combustion chambers featured special coatings that helped reflect heat back into the combustion process, improving efficiency while protecting the aluminum structure from thermal damage. The engine's contribution to vehicle dynamics went beyond simple power delivery. The W16's compact dimensions allowed it to be mounted low and forward in the chassis, optimizing weight distribution. The engine's mass, while substantial at 490 kilograms, was concentrated in a compact package that minimized polar moment of inertia. The smooth power delivery and linear torque curve made the enormous performance accessible to drivers without professional racing experience. This accessibility was crucial to Bugatti's vision of creating not just a powerful engine, but a usable supercar. The cultural impact of the W16 extended beyond the automotive world. The engine became a symbol of human achievement, proof that engineering could overcome seemingly impossible challenges. It appeared in countless videos, articles, and discussions about the limits of technology. The number 1001 horsepower entered popular culture as a benchmark of extreme performance. The engine inspired a generation of engineers and enthusiasts, showing that with sufficient dedication and resources, boundaries existed only to be broken. The business case for the W16 was unique in automotive history. Volkswagen Group reportedly lost money on every Veyron sold, despite the car's €1 million price tag. The W16 engine alone cost more to produce than most complete luxury automobiles. Yet the program was considered a success because it demonstrated Volkswagen Group's engineering capabilities and elevated the Bugatti brand to unprecedented heights. The W16 became a halo product whose influence extended across the entire Volkswagen Group portfolio, inspiring engineers and establishing technological leadership. The testing protocols developed for the W16 advanced automotive engineering methodology. The extreme conditions under which the engine operated revealed failure modes and wear patterns that wouldn't appear in conventional testing. The data gathered from W16 development influenced testing procedures across the industry. The sophisticated data logging systems developed to monitor the engine's operation during testing captured millions of data points, creating a database of high-performance engine behavior that continues to inform engineering decisions. The cooling system's sophistication extended to its control strategy. The system didn't simply react to temperature, it anticipated thermal loads based on driving conditions. The ECU monitored throttle position, vehicle speed, ambient temperature, and numerous other parameters to predict cooling needs and adjust pump speeds and fan operation accordingly. This predictive cooling strategy prevented temperature spikes that could trigger power reductions or component damage. The system could even detect partial blockages in radiators and compensate by adjusting flow rates through other cooling circuits. The spark ignition system represented another technological frontier, with 16 cylinders firing up to 6,000 times per minute in total. The ignition system needed to deliver precise, powerful sparks under extreme conditions. The coil-on-plug ignition system used specially developed coils capable of generating spark energies exceeding those of conventional systems. The spark plugs themselves were iridium units, specially designed for the W16's combustion characteristics. The ignition timing strategy was incredibly complex, with the ECU adjusting timing for each cylinder independently based on knock sensor feedback and combustion pressure monitoring. The exhaust system deserved recognition as an engineering achievement in its own right. The 4 turbochargers meant complex exhaust routing, with each turbo fed by 4 cylinders. The exhaust manifolds were investment cast from high-temperature stainless steel alloys developed for aerospace applications. The post-turbo exhaust system needed to handle gas temperatures that could exceed 900 degrees Celsius while meeting noise regulations and providing appropriate back pressure. The catalytic converters used sophisticated ceramic substrates coated with precisely controlled amounts of platinum, palladium, and rhodium to achieve the required emissions performance. The engine's influence on automotive electronics was substantial. The W16's ECU pushed the boundaries of automotive computing power, processing capability that would influence the development of engine management systems across the industry. The software development process, involving millions of lines of code and thousands of hours of calibration, established new methodologies for complex engine control. The diagnostic capabilities built into the system set new standards for fault detection and predictive maintenance. The air intake system was a masterpiece of fluid dynamics. Air entering the system passed through specially designed filters that could remove particles while minimizing restriction. The intake plenums were tuned to enhance cylinder filling at specific RPM ranges, using Helmholtz resonance principles. The throttle bodies, 4 of them in total, were electronically controlled units that could modulate airflow with millisecond precision. The entire intake system was designed to minimize turbulence and maximize volumetric efficiency, crucial for achieving the power density required. The global supply chain required for the W16 was extraordinary. Components came from suppliers across Europe, each specializing in particular technologies. The turbochargers came from Honeywell Garrett, the fuel injectors from Bosch, the titanium connecting rods from specialist suppliers using aerospace manufacturing techniques. Coordinating this supply chain, ensuring quality consistency, and managing the logistics of low-volume, high-precision components required sophisticated systems and processes. Many suppliers had to develop new capabilities specifically for the W16 program. The engine's thermal management extended beyond liquid cooling. The engine bay ventilation system used sophisticated aerodynamics to extract hot air while maintaining the vehicle's overall aerodynamic efficiency. Special heat shields protected sensitive components from radiation, using materials developed for aerospace applications. Even the engine oil served a crucial cooling function, with special passages directing oil flow to critical hot spots. The integration of all these thermal management systems required sophisticated modeling and extensive real-world validation. The manufacturing quality control processes were unprecedented in automotive production. Every critical dimension was measured multiple times during assembly. Torque specifications for bolts were not just specified, but electronically verified and recorded. Each engine had a complete build record documenting every component, every measurement, and every test result. This traceability meant that if an issue arose in service, engineers could trace it back to specific components or assembly procedures. The quality control process added significantly to production time and cost, but was essential for ensuring consistency and reliability. The W16's influence extended to automotive marketing and brand positioning. The engine became central to Bugatti's brand identity, featured prominently in advertising and communications. The technical specifications became part of popular culture, with Quad-turbo W16 entering the lexicon of automotive enthusiasm. The engine elevated not just Bugatti, but the entire Volkswagen Group's reputation for engineering excellence. Competitors were forced to respond, leading to an arms race in hypercar performance that continues today. The service infrastructure required for the W16 was unique in the automotive world. Bugatti established a network of specially trained technicians equipped with specific tools and diagnostic equipment. Service procedures were documented in extraordinary detail, with step-by-step instructions for even routine maintenance. Special transport containers were developed for shipping engines for major service. The global support network ensured that W16 engines could be properly maintained regardless of location, crucial for a car sold to customers around the world. The engine's contribution to materials science shouldn't be underestimated. The development program pushed suppliers to create new alloys, coatings, and composites. The valve seats used special materials that could maintain their properties at extreme temperatures. The piston rings featured advanced coatings that reduced friction while maintaining sealing under extreme pressures. These material developments found applications beyond the W16, advancing automotive and industrial technology more broadly. The calibration process for the W16's engine management system was an enormous undertaking. Engineers spent thousands of hours on dynamometers and test tracks, optimizing fuel injection, ignition timing, and boost pressure for every conceivable operating condition. The calibration needed to account for variations in fuel quality around the world, different atmospheric conditions, and the aging of components over time. The result was an engine that could deliver consistent performance, whether in the heat of Dubai or the cold of Scandinavia, running on 98-octane European fuel or 93-octane American gasoline. The vibration management in the W16 was remarkably sophisticated. Despite 16 pistons reciprocating at high speed, the engine was remarkably smooth. This resulted from careful attention to balance, with the crankshaft and all rotating components balanced to extraordinarily tight tolerances. The engine featured sophisticated harmonic dampers that absorbed vibrations before they could propagate through the structure. The engine mounts used special hydraulic damping systems that could adapt to different frequency vibrations. The result was an engine that could deliver massive power without the harshness typically associated with high-performance power plants. The electrical system supporting the W16 was substantial. The alternator needed to generate enough power for the engine management system, fuel pumps, cooling pumps, and other accessories while maintaining charge in the battery system. The wiring harness contained hundreds of conductors, each specified for its particular current load and operating environment. The electromagnetic compatibility engineering ensured that the high-energy ignition system didn't interfere with the sensitive electronic control systems. Even the grounding strategy required careful engineering to prevent electrical noise from affecting sensor readings. The engine's packaging efficiency was remarkable given its complexity. Despite having 16 cylinders, 4 turbochargers, and associated cooling systems, the complete power unit was surprisingly compact. This packaging efficiency resulted from careful component integration with systems nested within each other to minimize space usage. The turbochargers were tucked into the valley between the cylinder banks. The intercoolers were integrated into the intake plenums. Every cubic centimeter of space was utilized, resulting in a power density that remains impressive even by today's standards. The development of special tools and equipment for the W16 represented a significant investment. Special fixtures were needed for engine assembly, ensuring precise alignment of components. Diagnostic equipment was developed specifically for the W16, capable of reading the hundreds of sensors and analyzing the complex data streams. Even seemingly simple tasks like changing spark plugs required special tools due to the engine's packaging. This specialized equipment was distributed to authorized service centers worldwide, ensuring consistent service quality. The engine's influence on racing technology was indirect but significant. While the W16 itself never powered a competition car, technologies developed for the engine influenced racing applications. The advanced turbocharging strategies, sophisticated cooling systems, and engine management technologies found their way into motorsport. The demonstration that reliable 1,000 horsepower engines were possible influenced the development of hypercars that bridged the gap between road and race cars. The W16 proved that road car technology could match or exceed traditional racing technology in certain areas. The environmental testing of the W16 pushed into extreme conditions. Engines were tested in climate chambers that could simulate everything from Arctic cold to desert heat. Cold start testing at -30 degrees Celsius validated the engine's ability to start and run smoothly in extreme cold. Heat soak testing in 50-degree ambient temperatures ensured cooling system adequacy. Altitude testing validated performance at elevations where naturally aspirated engines would lose significant power. This comprehensive environmental validation ensured that the W16 could perform anywhere in the world its owners might take it. The engine's contribution to automotive safety was subtle but important. The massive power required sophisticated traction control and stability management systems to be usable safely. The development of these systems for the W16 advanced the state-of-the-art in vehicle dynamics control. The engine's smooth power delivery and predictable response characteristics made the enormous performance more manageable for drivers. The extensive testing required for the W16 also validated safety systems under extreme conditions that wouldn't be encountered with conventional engines. The documentation created for the W16 program filled thousands of pages. Technical specifications, test procedures, service manuals, and training materials represented an enormous knowledge base. This documentation preserved the engineering knowledge gained during development, ensuring that future engineers could understand and learn from the W16 program. The thoroughness of this documentation reflected Bugatti's commitment to supporting the engine throughout its service life, potentially decades into the future. The W16's influence on automotive enthusiasm cannot be overstated. The engine inspired countless young people to pursue careers in engineering. It demonstrated that automotive engineering could still push boundaries and achieve the seemingly impossible. The engine became a benchmark against which other high-performance power plants were measured. Online forums and communities formed around discussing and analyzing the W16's technology. The engine achieved a cultural significance that transcended its technical specifications. The precision manufacturing techniques required for the W16 advanced the state-of-the-art in automotive production. The honing process for the cylinder bores achieved surface finishes measured in fractions of microns. The valve seats were machined to tolerances that required specialized measuring equipment to verify. The assembly process required clean room conditions typically associated with semiconductor manufacturing. These manufacturing advances influenced production techniques across the automotive industry, raising standards for precision and quality. The engine's thermal efficiency, while not its primary design goal, was remarkable for such a high-performance application. At part throttle, the W16 could achieve thermal efficiencies approaching those of conventional engines despite its enormous power capability. This efficiency resulted from advanced combustion chamber design, sophisticated fuel injection strategies, and careful optimization of compression ratio and boost pressure. The ability to extract such massive power while maintaining reasonable efficiency under normal driving conditions represented a significant engineering achievement. The acoustic tuning of the intake system went beyond simple noise management. The engineers used the intake sound as a form of driver feedback, with the note changing character as the engine moved through its rev range. The transition from the lower-pitched rumble at idle to the complex harmonic at full power provided auditory confirmation of the engine's state. This attention to the sensory experience of the engine reflected Bugatti's understanding that emotional connection was as important as technical capability. The durability validation of the W16 included accelerated aging tests that simulated years of use in months. Engines ran continuous cycles that replicated the most severe usage patterns, from repeated maximum acceleration runs to extended high-speed cruising. Components were subjected to accelerated corrosion testing to validate long-term durability. The validation program was so comprehensive that Bugatti could confidently offer a warranty on an engine producing power levels that would have been considered racing only just years before. The engine's influence extended to the broader Volkswagen Group portfolio. Technologies developed for the W16, from advanced turbocharging to sophisticated engine management, influenced engines throughout the group's brands. The knowledge gained from pushing to extreme performance levels informed the development of more mainstream power plants. The W16 served as a technology demonstrator whose benefits extended far beyond the limited production of Bugatti vehicles. The global recognition achieved by the W16 transcended the automotive industry. The engine appeared in engineering textbooks as an example of pushing technological boundaries. Museums sought examples for their collections, recognizing the W16 as a significant artifact of early 21st century engineering. The engine won numerous awards and accolades, from technical innovation prizes to recognition for its contribution to automotive culture. This recognition validated the enormous investment made in the engine's development. The W16 engine stands as perhaps the most significant milestone in internal combustion engine development of the 21st century. It proved that the boundaries of what was possible in a road car engine were far broader than anyone had imagined. The technologies developed, from advanced materials to sophisticated control systems, influenced automotive engineering globally. Most importantly, it demonstrated that with sufficient vision, resources, and engineering excellence, humans could achieve what seemed impossible. The Bugatti W16 didn't just break the 1,000 horsepower barrier, it shattered preconceptions about what automotive engineering could achieve, inspiring a generation of engineers and enthusiasts to push ever further into the realm of the extraordinary. The legacy of this remarkable engine extends beyond its impressive specifications to represent a monument to human ingenuity and the relentless pursuit of engineering perfection. As we stand on the cusp of an electric automotive future, the W16 may represent the ultimate expression of internal combustion technology, a fitting culmination to more than a century of development in reciprocating engines. Its achievement will be remembered not just for the raw numbers, but for the elegance with which it achieved them, proving that even at the extreme edges of performance, engineering excellence means creating something that is not just powerful but refined, not just capable but reliable, and not just functional but inspiring.